the ball bouncing question. You guys are equipped to do this. Might take a little bit of thinking. Hoping you are not feeling thinking averse today. I'm going to get something set up here while you guys are working on number 6. Really interesting to see the different thoughts you guys came up with. I think you're doing really well. And I really like questions like this where there's kind of more than one way to think about it. So I didn't see this presented exactly like this. I might just not have looked over your shoulder at the right time. But here's my thought process on this one. I didn't see a whole lot of this, but for me, to help with this, I think I would try to picture it and just draw a very rudimentary picture of what's actually happening. So maybe if this is the ground right here, the ball starts up here, 6 feet high, from there to there, and it drops down and hits the ground, it's going to bounce up, right? And so I'm thinking when it bounces back up, this distance here is going to be 3/4 of 6, and this distance here is going to be 3/4 of 6. That make sense? And then maybe I do another bounce in a different color. This would be 3/4 of 3/4 of 6, and this would be 3/4 of 3/4 of 6. That make sense? And as you continue on with the various bounces, basically an extra 3/4 would be multiplied times each side of the bounce. So then how does this work as far as trying to figure this thing out? My first thought is, well, I know for sure that on the first drop, the ball is going to travel a distance of 6. So I'm going to just put that in there right away and say it's going to be 6 plus, and then hopefully the thought is you see that it's going to have to be a summation, right? Because the ball is just going to keep bouncing and bouncing and bouncing and bouncing, seemingly forever. And so I got to turn my various bounces into a sigma and try to get this set up right. So the first one is 3/4 times 6, 2 of them, right? So I'm going to say, I'm going to be thinking here, this is really 2 times 3/4 of 6. Actually, let me do a better job of color coding this. So this is going to be 2 times 3/4 of 6. Then this one is going to be 2 times 3/4 squared of 6, right? And presumably, wouldn't the next one be 2 times 3/4 cubed of 6? So I'm going to put plus ... plus 2 times 3/4 to the n of 6. Does that make sense? So that's going to be the element that I put into my sigma. So I'm going to say that and I'll use the letter I to be my summation element. And I want I to go from something to... How many times is this thing going to bounce? Theoretically. Say again? And how many bounces would that take if it's 3/4 of the previous one every time? It would be infinity, right? That's where this one goes from being theoretical to like the practical side. Does it ever stop bouncing on an atomic level? Maybe not. Who knows, right? But we're not going to go there necessarily. So we're going to say I equals something to infinity. And so let's see here. I would want my first I, in this case, to be 1, right? Because the very first one is 3/4 to the 1. So I'm going to say I equals 1 to infinity. Make sense? This is my drop right here, and this is all my bounces. So it dropped 6, and then from there on out, it's going to bounce 3/4 of the previous one each time. So how do I finish this up? I'm going to say 6 plus 12 sigma from I equals 1 to infinity, that's supposed to be an infinity, of 3/4 to the I. Okay, so then we were talking about this in the back. You guys recognize what kind of series that is with the sigma of 3/4 to the I?
Geometric.
It's geometric. Is it going to converge or diverge? How do you know it's going to converge? Yeah, the absolute value of that common ratio less than 1. We know it's going to converge. So what we can do is then say, well, I can replace that entire sigma with what I know the geometric summation to be. And that would be the first term, which is 3/4, over 1 minus the common ratio, which is 1 minus 3/4. We do a little arithmetic with that. 6 plus 12, that would be 3/4 over 1/4. So that's really 3, and 6 and 12 times 3 is 36, plus 6 is 42. So 42 feet, I guess it would have to be. 42 feet for the amount of distance that the bouncing ball actually traveled. Jasmine, question?
So, these questions, would you say it's easier if you draw it out?
So I can't say what's easier for you. I can say what's easier for me. Like I wanted to draw that thing out and say, all right, what exactly is the ball doing? And then try to formulate it into a sigma versus like trying to go from like a blank canvas and say, well, I got this 3/4 thing. And I personally feel like I would forget stuff or not see things. When I see the picture, I'm like, oh, 3/4 of 6, 3/4. Okay, there's 2 of those, and there's 2 of those, and there's 2 of those. And then I'd start to build it out and then get it into a sigma versus starting with a sigma. That's just me. You might look at that and disagree, and I'm okay with that. But that, for me, that's my personal recommendation.
Why isn't it supposed to be A over 1 minus R?
Yeah.
Why do you have R over 1 minus R?
I know, I do have A. I started my sigma at 1.
Oh, okay.
And so, I mentioned that a little bit. I was like, what do I want my low number to be? Do I want it to be like 0 or 1 or 2 or 3? And I looked back at my picture and I realized that when the ball started bouncing, it was 2 times 3/4 to the first, not 2 times 3/4 to the 0.
Okay.
There are different ways of looking at it. Like I know that Colin and Jaden back there, they did start their sigma at 0, but then they subtracted off the extra 6.
Mm-hmm.
Right? They realized, hey, the ball didn't like go up first; it started up. So they added in too much and then subtracted off the overage to account for that. That made sense too. So these are lovely questions, right? And you can think about it a couple different ways. That's what they thought. I did it a little different. It's okay. It's about being able to understand what you did. Any other questions? Okay, fair enough. So let's just do a really, really brief review. Let's remember why we study this kind of thing. Primary reason for us right now is simply this. In the next weeks and months or so, literally, we will be studying how you can take some function or graph of a function that didn't come from a polynomial. It came from like e to this or sine of that or cosine of something or arctangent or ln or whatever, something that's not a polynomial, and then taking that and expressing it as a polynomial, which I hope we all agree that that's a good thing, right? It's way easier to handle polynomials than it is ln of 1 plus x quantity squared or something like that. It's always easier to do polynomial stuff. And so to be able to understand how good a fit that polynomial is to this crazy sine of whatever curve, we've got to have a good understanding of what that end behavior looks like with these series. And since there are lots of different ways series can go, we have to have lots of different ways to deal with them. Like I said, I think last time, I think there's like 7 or 8 of these series tests that we will look at and some little corollary things that kind of go along with. And so, one more second. So don't forget though. Last time we looked at a couple of different tests. We looked at the nth term test. And remember, the nth term test was that mean coach. They only tell you when you mess up. They never tell you when you do it right. So the nth term test will only tell the series that it diverges. If the series might converge, it just stays silent. And then the other test we looked at was the geometric series test, which we kind of sort of used here. Dylan, your question.
Yeah.
So what situations, I guess, would you be talking about when you say it's easier to use a polynomial? Because I don't know, it kind of scares me to look at it as summation and think that probably some
Yeah.
easier than a summation.
So I'm talking about like the written out polynomial. So I get, yeah, sometimes the sigma thing, we'll want to get comfortable with the sigma, and we'll keep using it. I think you'll get more comfortable with it. But I'm talking about, say, for instance, this. This is a classic.
Okay.
Good luck. You'll need lots of it. It's not going to happen. However, if we could say that this is supposed to be an approximately, probably one of the worst approximates ever. There we go. If we could say that the thing I'm about to write is approximately, and we can control the degree of approximately ourselves, approximately equal to would you not agree that that would be easy? Just do a handful of power rules, 60 seconds later you're done. Versus sitting here and staring at this for hours and Googling it and not even understanding what came up on Google. Zeta function, what? Or whatever, you know? So yeah, so you get into these really nasty antiderivatives. And one of the strategies will be, whether it's an indefinite integral or a definite integral, one of the strategies will be, well, hey, let's just use a polynomial approximation and let's control our error. Let's make the error within what is acceptable to us for whatever reason we've decided and go with that instead of that. Have you ever wondered how Math 9 works? You think there's so much memory in your calculator that it knows like all of the integrands you might possibly put in there and all the different limits you might conceivably ever, I mean, there's got to be some pattern to it, right? And they don't use an exact power series like we're going to do, although that's what they used to do, but that even took up too much memory. So there's a new-ish in the last like 20, 30 years version of a series that they use to help approximate for Math 9. So, so you start to see even with like some high school student trying to pass the AP test, even if they're just doing AB, they're not even doing what you guys are doing. Math 9 series matter, right? Your calculator uses a special type of series to do that stuff. It's easier than trying to figure out all the different functions some crazy high school student might try to put into Math 9. No one's going to think of all those. So anyways, that makes sense? Okay. So anyway, so today we're going to take a peek at a couple of others, one of which you've already seen. So let's do that. And we'll just see how this goes. We obviously have a shorter class than I had anticipated. So let's do this. We might not get to all the examples, and that's okay. We'll just roll with it. So we're going to look at two new series tests here. The first one is called the integral test, and the second one is called the p-test. We did look at the p-test when we did those improper integrals back, I don't know, whenever it was, November, I think. And so it is the same p-test. So that's maybe good that you have a little bit of momentum maybe left over from that. The integral test is something new, but the integral test is based on those improper integrals. And so you should have some good background for that. Why don't you read that over? I've highlighted some stuff. And I'm going to make a couple of points here, and then I want to try to prove some things for you. So it says, for the integral test, the conditions are f has to be positive. We'll talk about positive, continuous, and decreasing, at least eventually decreasing, for x greater than or equal to 1, and if a sub n, are you guys comfortable with a sub n being kind of like the nth term for a series? So if a sub n could be represented by some function f of n. We're saying that they're the same thing, so they could be used interchangeably. So if we take those conditions, then here's what we can say. Sigma, so the summation, the actual full summation of the series, and the improper integral from 1 to infinity, they're either going to both converge or both diverge. In other words, whatever one does, the other will follow. but I put not necessarily. I'm going to say not hardly ever to the same value. So this is a situation we're going to apply when the nth term of the series is easily integrated, right? So just a quick integration, we can do an improper integral real quick and get a sense of convergence or divergence. We're not going to do this with something that's really difficult to find an antiderivative of, because you got to be able to do the integral, right? You got to be able to do the integral to do the integral test. So can I prove this one to you guys, or try to prove this one to you guys? Okay. So I wanted to write this up here just to kind of get us started. What's interesting about this is you look at the series there on the left, sigma from 1 to infinity, and we want to think about its relationship to the function, the continuous function, that is going to be the thing we do the antiderivative of. So would you guys agree with me that the actual summation of the series will be represented by rectangles? Couldn't the summation of the series either be a left sum, like that? I put a little dot, dot, dot to signify there's a bunch of other ones in there, but we'll just kind of write that end one in there. Or couldn't it be a right sum also? Let's try that again. Like so, and then this one would be about like that. So I want you guys to get the sense of what the integral test is saying. The integral test is saying if you do the improper integral from 1 to infinity of the blue graph and the red graph, they're the same thing, and you do that improper integral and you get a number like 10, some real number, that means that the series also converges, just like the improper integral. But if the improper integral diverges, then the series also diverges. So there can be a little bit of confusion here. So think about this. If I told you that the integral of the blue curvy graph diverged, can you guys see how the series, which is an overage, would also diverge? Like if the area under the blue graph is heading towards infinity, can you see how the blue rectangles would be even more towards infinity? But then the hard part is, what if the blue graph converges to actual real number? Well, then you would say, wait a minute, the series is a little bit bigger, and is it a little bit too much too bigger, right? Therefore heading towards infinity. Like, how do we reconcile that? So check this out. If I was going to write out a relationship here for the blue graph, maybe I'll do it like this. So if I said sigma of a sub n and the integral from 1 to n plus 1 of f of x or f of n. And let's see here, I would start this at 1. I'll make this a sub I, how about? 1 to n. What would be the relationship there? Would the series be bigger than the definite integral, or would it be the other way around? Which one's going to be bigger for the blue graph? What do you think? She says integral. You guys agree or disagree? Which one's bigger? You see how the rectangles are higher than the curve at every spot? So wouldn't the summation of the series be greater than or equal to the integral? Notice it's not making sense? Liz, you're giving me I don't know look.
Is the sigma like...
The sigma stands for the summation of the terms in the series.
Okay.
So like the first, like this area would represent a sub 1. That would be your first term, right? Because it's 1 times whatever that height is.
Mm-hmm.
This would be a sub 2, like this whole rectangular area. This would be over here, this would be a sub n.
And then the integral is like the actual...
The actual
Exact.
area between the x-axis and the curve.
So then how do you say if you're doing, a right sum or a left sum? Is it just where the I starts?
Yeah.
Okay,
Yep, did you start on the far left edge or on the right edge?
okay.
Yeah, we'll do the right sum here in a second. So are you guys okay with the idea that if you took all the sum of all the terms in this series, it would be bigger than the area under the curve? It goes back to if you have a left sum on a decreasing graph, isn't the left sum an over approximation? That's really what this is. Question?
I guess I just don't understand why are they rectangles and not just like infinite?
So when you do, like when you write out the sum, the terms of a summation. So let's do this. Sigma from I equals 1 to 10 or something, right? And let's say that it's, let's do a geometric series since we've been doing those. Let's say it's 7/8 to the n. Wouldn't this be 7/8 to the first times 1? There's your times 1. Plus 7/8 squared, that's supposed to be a 2, times 1. So each of those rectangular areas would represent like the whole term. And then you'd add the next term, and then you'd add the next term. Therefore, getting the actual sum of the series, which in this case is bigger than if you just did the integral of the curve. Make sense? So then over here, it's a little bit different. Let's go sigma, and over here it's going to be integral from one to n. And let's see here. The hard part about this is I cannot, like my series doesn't start at 1, does it? Where does it start? Like the value of the first term would actually start when n is 2, right? See? The height of the rectangle is based on the height at 2, not the height at 1. So I'd have to say I equals 2 to n of whatever that element is, you know. How would these two relate? Which one's bigger? The integral is bigger this time, right? Because we're doing a right sum on a decreasing graph. And so we would say this. So I want to try to put this together. And I can see this is, this is pretty similar to this. And this is pretty similar to this too, but the fact that it's I equals 1 and I equals 2 is going to turn out to be a pretty big deal. So I have a question for you. Can you guys think of any way that I could turn this, without breaking any rules, turn this into a situation where I started at 1? So I could have a double comparison. What could I do to this relationship to make this get to a place where I just equaled 1? What do you think?
So make it I equals 1 to n minus 1? Like subtract 1 from your start and end?
But that's not really true though, because we didn't use, we never used 1 for a height, right? And we never used n minus 1 for a height either.
Didn't we if we got to n? If we got to n, we would have had to pass through n minus 1.
Yeah, but we didn't use it to generate the height for a series term.
So did we never use 2 as a height either?
Oh, we used 2, it's right there.
So how did we never use n minus 1?
Notice how n minus 1 doesn't actually intersect the curve, but 2 does.
So did we use 3 as a height?
Yeah.
So wouldn't there be a bunch of rectangles in those dot 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 areas?
Sure. So this one would be based on 4.
Mm-hmm.
This one would be based on 5, right? But to get the actual area, you're using the right edge. You're wanting to shift it over to the left edge by starting at 1. That would be the main issue. Like, did we ever use 4? Of course we did. Did we ever use 5? For sure, but we never used 1. That makes sense?
Mhm.
This is kind of a tricky step. Maybe you can come up with it, maybe not. I don't know. What do you think?
Could you do that, you said I equal to 1, then the top equal to n, but you said I, a to the I plus 1, like a sub I.
Yeah, but so the problem with that is I want to get to a place, and you don't maybe understand why yet. I want to get to a place where this and this are exactly the same. I want them to be the same, exactly. Let me rephrase the question. When I compare this to this, what's missing from this one? Say again? The one? Like, okay, I'll rephrase again. Which term, and Colin, you might be right, you're just not saying it the way that I'm hearing it. Which term is missing from this one that's actually present in this one? How would you, like symbolically, what would you call it? A1. And I wasn't sure what the one meant, so check this out. Let me scooch this over. Let me scooch this over here. So this is here, this is here. Remember, this is a relationship, like an equation, inequality, that kind of thing. And remember, whatever you do to one side is okay for the most part, as long as you do the same thing to the other side, right? So what if I did this? What if I said, let's just add, so I'll put this in parentheses, let's just go plus A1. And as long as I also do this, I haven't broken any rules. I just added some real number to both sides. So then, if I take this sigma, which was missing this term, and add that term to it, can I now write it like this? Sigma from I equals 1 to n of a sub I. I just added the one term that was missing.
Yes.
I was missing, as Colin put it, the 1. I just added it in there so I could rewrite it in the way that I wanted. And then, of course, this would remain the same. La, la, la. And I still have this plus a sub 1 over there. Why is this so darn important? What I can do now is I can take those two statements and I can write them into one. So what I can say is, let's see here, I can say that the integral from 1 to n plus 1, I'm getting this from right here, of f of x dx is less than or equal to the summation and I know from the second statement that this I should say, is less than that. So it would be 1 to n of f of x dx plus a1. We did all that to get that relationship, and believe it or not, we're almost done. Making sense? Questions? All right, so then what we're trying to talk about here, of course, is what is going to happen with the series when the number of terms gets bigger and bigger and bigger and bigger. We're talking about n heading towards infinity. So check this out. If I say I am interested in what's happening long term, I'm going to do the limit as n goes towards infinity of all this. Here's what it would look like. Sigma from 1, and of course infinity plus 1 is just infinity. F of x dx is less than or equal to sigma from I equals 1 to infinity of a sub I. And then of course I get the same sort of pattern going on over here, plus a sub 1. Okay, so this is where we can make a logical, very small, but a logical leap. Think this through. If, and did you guys notice that this now and this right here are now the same? Of course we have the plus a sub 1 over there. Check this out. If this diverges, let's say we do our improper integral and we go through the steps and we come up with infinity, right? We come up with a diverging answer. Can't we then say, if this diverges, this series being a little bit bigger than that, doesn't this have to also diverge? Make sense? Okay, so then if this converges, then this also converges. And then we have to admit, so let's say that this converges to some real number, like 5 or whatever. So you could say, all right, well, 5 is less than the summation, but the summation is a little bit bigger than that, right? Yes? Summation. So you might be stuck on this and say, well, wait a minute, just because this converges, why does that mean that this also converges? You can see why somebody's stuck there, because this is bigger than that. Well, now we've got to look at the other side and say, well, then this is actually smaller than this whole right side. And so if this converges, this being a little smaller than that, doesn't this have to also converge? Make sense? And this brings in the idea of why the terms have to be only positive. Think back to all your work with inequalities in the past, and especially considering this a sub 1 thing. If you had positive and negative terms in there, do you see how this inequality relationship could get turned upside down? So that's why that's one of the conditions. If this was a negative number, or you had positives and negatives going back and forth on these, that's going to change the relationship of the inequality and really making this invalid, right? Especially when you think about this. It would flip the whole thing around, and it wouldn't make any sense. So this is dependent on your function describing your series being positive for all terms. Liz, your question.
So, are you kind of saying, like, if the left side, if the leftmost one converges or diverges, that means that the rightmost one converges or diverges?
Sure, yeah. Because isn't the rightmost one simply that plus some finite number?
Oh, yeah, okay.
And so this is a little bit bigger than that. I'll give you that. But it's the same expression, and so the convergence or divergence of the two integrals will be the same. But this plus a sub 1 makes it a valid comparison and also allows us to compare both divergence and convergence for this. The whole point of this is to help you understand why it works, how it works. Maybe expand your minds a little bit just on like mathematical proofs too. The bottom line, like the big takeaways are the conditions have to be met. Right? We didn't really talk about the decreasing thing yet. I think that's mildly self-apparent, at least to a degree. Because if the function is increasing, you're going to get divergence, right? I mean, that's one way of looking at it. Go a little deeper than that. The conditions have to be met, and then whatever the integral does, the series will do the same thing. So if the integral converges, the series will also converge. If the integral diverges, the series will also diverge. Is it really time to go? Okay. So guys, I guess we don't have class till Wednesday morning. So on Wednesday morning, what we'll do is we'll do some examples with this, right? You'll be able to see kind of this integral test in action. No, we have a quiz on Wednesday. It's a polar quiz, isn't it? Yeah, polar quiz. So I guess on Thursday we'll see this in action.
Can we come in early at all?
Yeah, no coming in on early quiz. It's no test. Right? It's a polar quiz. Am I right?
Yeah.
That's what I was remembering. Okay. So yeah, we'll pick this up again on Thursday. So hope you guys have a wonderful day. Sorry, our class was cut short because of the late start. That made sense though. So have a wonderful day. See you guys.
I don't see why they do it.
No, stop.